Right, we haven't spent a lot of time in lectures on interpreting word problems as differential equations, so we're going to do that here. We're also going to do this in several different units and formats, and we'll talk about the good ways to do that. So this is a classic mixing problem. We have salt water. My mouth waters the whole time I think about this problem, so I apologize if yours does too. We start with Q 0 grams of salt in 1,000 liters of water in a tank. Um, Q0 is just some constant, and then for t greater than 0, this just means starting at the beginning. We have some solution of salt water poured in. It happens to be 100 grams per liter of salt in this solution. It's poured in at a rate of r liters per minute. R is some other constant. And then this is maybe not realistic, but it says the solution is immediately well mixed, so it's just poured in and immediately um, there's not more salt in the place that it just got poured in. Um, and then also for t greater than 0, the solution is drained. So poured in, well mixed, and then the new concentration is drained out at the same rate that it's poured in, so there's always 1,000 liters of water in the tank. And it says to model the solution as an initial value problem. Okay, so let's do the easy part, which is Q0. So we have big Q is the number of grams of salt in the tank. So at the beginning, we have Q0. That's the easy part. And then this equation is in grams. It's good to keep track of units here. Okay, and then we need a differential equation, meaning something to do with the change, dq by dt. This is going to be in grams per, let's look at the time units. They're all in minutes, so that's good. We don't need to convert anything. Always good to check. All the volumes are in liters. All the masses are in grams. So we don't need to do anything funny there. This is going to be in grams per minute. So the change in grams of salt in the water tank every minute. Okay, so there is some salt coming in, and there is some salt going out from the draining. So how much is coming in? Well, we have 100 grams per liter, and we have r liters every minute. So let's just look at those units. 100 grams per liter. If we multiply that by r liters per minute, then we see that the liters cancel, and then we get 100 r grams per minute. So that is our rate of salt coming in. 100 r grams every minute. And then how much salt is leaving. The solution is well mixed, so we don't know how much salt is in there, except we do. The amount of salt in there is Q of t. So we subtract Q of t grams total in there in 1,000 liters. So the concentration is Q over 1,000 grams per liter. And then same thing, we're going to multiply by being drained at r liters per minute. And same thing, the liters cancel out, so we're left with big Q times r over 1,000, and this is now in grams per minute. So that's good. So there's the differential equation. There's this one. This is the initial value. There's your initial value problem. Takes a minute to think about. It's maybe very frustrating on a quiz or test where you feel like you should be writing the whole time, but when you have a word problem and you want to interpret it, thinking for a few minutes can be good, and you may not be writing very much, and that's fine. You're doing it right. Okay. If you want to change units and do this for different things, couple ways to do it. One is to start the problem from scratch, and one is to take the equation you already have and convert units. So for number 2, it's easy to start from scratch, so I'll show that from scratch, and for the rest of them, I'll convert units. So this is little q of t in kilograms now. And we go back and look at the problem. There's only 2 things that are in grams, so we'll just convert that in the problem to kilograms. We have Q0 over 1,000, right? You should have fewer kilograms than grams, so the dividing is right. We start with Q0 over 1,000 kilograms, and then this concentration is now 0.1 kilograms per liter. So we can do the exact same thing. Little q of 0 is now Q0 over 1,000. And then the differential equation is dq by dt, little q now. Now we're in kilograms per minute. And then everything is the same except this 100, right? This calculation only depended on the mass in the tank at the moment, which is now going to be little q of t. So we're just going to do the same thing but in different units. So this is going to be 0.1 times r minus now little q times r over 1,000. The units are subsumed into this q, so this looks exactly the same as this term. This one is different because the units were in the 100, so now that's 0.1. So there's our initial value problem for kilograms. If you don't like this, instead of starting from scratch, you could have said, well, q of t is big Q of t over 1,000. And then substitute that in. You can get dq by dt by differentiating both sides of this is 1 over 1,000 big dq by dt. So you can get the differential equation from there as well. For this one, we will actually do it that way because I find it difficult to think about concentration from scratch. So what does concentration mean? Well, big Q of t was the number of grams, so the concentration must be the number of grams over the total volume, which is always 1,000. Okay, so then this dc by dt, we're going to differentiate both sides, is going to be 1 over 1,000 dq by dt. Okay, let's see. The initial concentration is Q0 over 1,000. Okay, so we have C at 0 is Q0 over 1,000. This is now, the units are now grams per liter. And then for dC by dt, the units for this equation are going to be grams per liter per minute, the change in concentration every minute. And then we're just going to use this. So it's 1 over 1,000 times dq by dt, which we already have. 1 over 1,000, and then I'll just sub this in. 100r minus q. If I multiply 1,000 to both sides, q is 1,000c. So I get 1,000c times r over 1,000. I'm just subbing everything from here into here. I swapped out the q for 1,000c. This cancels, and so I get dc by dt in grams per liter per minute is, if I distribute this 1 over 1,000, this is 0.1 r minus big C times r over 1,000. Notice this thing is still the same because the units are subsumed into the variable again. Okay, what if we wanted to do kilograms per liter? Then I would do the same thing, but I use the little q equation. Okay, so that's not hard. So mu of t, same thing, I have little q kilograms in the tank, so my concentration must be that over 1,000, the 1,000 liters. And then d mu by dt is 1 over 1,000 d little q by dt. I'm now in kilograms per liter. Mu of 0 is little q of 0 over 1,000. And little q of 0 was big Q0 over 1,000. So I've got Q0 over 1 million. Small number, but only because I've changed units. And then I'm now in kilograms per liter per minute for the concentration. D mu by dt is 1 over 1,000 times this one. So I actually get let's see if I can do this right, 0.0001 r minus, and then little q is 1,000 times mu, so those thousands will still cancel. So actually, this term will still stay the same. I'll still be left with mu r over 1,000 once I distribute this 1 over 1,000. You can check that out. Arithmetic is the same as up here. Okay, and then we're going to change one more thing. So to have less ugly numbers, we're going to go back to C. For C of t, we're going to do the concentration still in grams per liter, but now we're going to do time t in hours. So I have a couple options. I could go back to here again. Let's actually do that. So I could either say t, the new t, maybe actually I'll call it s. Actually, let's call it capital T. C of capital T at a time capital T in hours. Then I could say capital T is little t over 60, right? At little t equals 60, capital T should be 1. So I could substitute that. I might need the chain rule when I substitute that. So that's a little bit complicated. Maybe what I'll do instead is I'll just convert the question to hours. So if it's R liters per minute, what does that mean? That means I'm going to do 60 R liters per hour. For both of these, I have 60 R liters per hour. Okay, so then I'll do my calculations here. My C of big T. C of 0 is still the same. C of 0 is still Q naught over 1,000. That's still in grams per liter. Now I'm going to be in grams per liter per hour. Then dC by dt. Think of this, so if I had done this from scratch, this concentration would have been 0.1 times my R liters per minute. So this, instead, I'm going to have 0.1 grams per liter times 60 R liters per hour. And then the same thing will happen over here. I would have had my concentration over 1,000 times my R liters per minute of draining. So I'm just going to have 60 R liters per minute of draining there. And that'll be in grams per liter per hour. So dC by d, this is d big T. Change the variable. D big T is whatever that is, 60 over 10. Okay, so 6R minus, and then this is going to be 60 over 100, or 6 over 100, which is 3 over 50. So 3CR over 50. This equation is in grams per liter per hour. Okay, so that's a couple ways to change the differential equation into different variables. If it does not ask for you to write a new differential equation in a new variable, I think the easiest is actually probably to solve the original equation, which was a little bit easier to get to than these other numbers, and then just convert your answer to whatever units they want. However, if they do ask for an equation in different units, you can get there either through substitution or through converting the problem numbers and starting over.